title of this paper is Semi-Supervised Scene Change Detection by Distillation from Feature Metric Alignment. My name is Seonhoon Lee, and I conducted this research together with Professor Jong-Hwan Kim. SCD compares two photos taken at different times in the same place and divides the changed areas. At this time, the time interval between captured photos may be short or long. The longer the time interval, the greater the change in illumination or environmental conditions, such as night and day or summer and winter, for the same scene. This is problem definition. The input of the SCD problem is a reference and query image pair, and the task performed is to segment the changed parts between the pair images. At this time, the USCD model uses deep color as the base model, so it has optical flow and change map as output. The following is an overview of USCD, the proposed unsupervised SCD learning method. In this study, we assume a situation where there is no ground truth label in the target domain where SCD will be performed. Learning is divided into two phases: pre-training and fine-tuning. In the pre-training phase, supervised learning is performed only with the synthetic dataset, and in the fine-tuning phase, both the synthetic dataset and the target dataset are used to add the supervised loss and the unsupervised loss. Learning occurs through loss. To learn optical flow and change maps, I use the reconstruction framework. Flow maps maximize similarity by adjusting the viewpoint difference between two images, and change maps maximize similarity by masking and removing changed areas that do not exist in common between the two images. At this time, it is not advisable to simply calculate RGB similarity due to changes in illumination, due to the type gap between the two views or lighting effects due to differences in viewpoints. Therefore, designing a similarity metric well is important in this learning method. We used multi-level feature similarity with the following formula as the metric in my learning framework. The proposed similarity can simultaneously consider low-level details and high-level semantics by multiplying all the normalized backbone feature similarities calculated at each L level. After calculating the similarity maps at all levels, upsampling is performed again according to the resolution of the L4 level to obtain the finals map. Although the feature metric loss itself is capable of flow and change learning, it does not affect the loss even if the change probability value is estimated to be any value between 0 and 1 for pixels with d values close to 0, that is, pixels with high similarity. There is a risk of estimating a change map that is too overconfident. To solve this problem of feature metric loss, we introduce the following change regularization. Change regularization LCR is calculated as the product of the negative logarithm of the similarity map and the change probability map as shown in the formula. As the last component of the unsupervised loss function, we introduce edge-air smoothness regularization. This regularization prevents the change probability from changing too much as the pixel changes, while also allowing the change probability to change rapidly at object boundaries. Next is the supervised learning loss calculated on synthetic data. The flow map calculates the final hierarchical endpoint error by calculating the L1 loss for each feature level and then adding the weighted sum as follows. In the case of the change map, the final hierarchical focal loss is calculated by calculating the focal loss for each feature level and adding weighted sum. Supervised learning loss is calculated only for synthetic datasets with labels LM and LV. Lastly, we will explain consistency loss along with the entire training process. After fine-tuning, the student-teacher structure is formed using the parameters obtained through pre-training as initial values, and then learning is conducted. This structure is used to train the model to perform robust SCD tasks, even when the illumination change between image pairs is relatively large. The teacher network estimates the change map for the original data, and the student network estimates the change map for the data for which photometric augmentation has been taken, and then the student's change map is close to the teacher's change map. Synthetic datasets are created using cut-paste and random transformation. A change label is obtained by pasting a random foreground object into the background image, and a flow label V is obtained by applying a random geometric transformation to the image. The resolution of each image is 520 by 520, and the number of samples used for learning is 20,000. We use unlabeled target dataset for outdoor and indoor environment. Outdoor dataset includes tsunami and GSV, and indoor dataset is change sim, which is simulated warehouse environment dataset. The classification metric is the F1 score, which is calculated as the harmonic mean of precision and recall. The ablation study shows the proposed regularization methods and losses are highly effective. Next are the performance comparison results with models from previous studies. As a baseline for comparison, we used the supervised learning models introduced in the introduction. As a result, it was confirmed that it performed better on all datasets than the previous SOTA model, and this confirmed that the proposed USCD was effective. Second, it was confirmed that the proposed USCD had relatively equivalent performance compared to the fully supervised learning model. Ultimately, the proposed USCD has performance comparable to that of a supervised learning model, and in particular, the results show that it is possible to secure significant performance, even with a relatively small number of samples. Thank you for watching.